stick your hand up, I'll run over to you and you can speak into the mic. And with that, it's my pleasure to welcome Jari to the stage to talk about how to port JUCE plugins to web browsers. Thank you.
Okay, thank you. So, as we all know, JUCE already provides as support for all major desktop platforms and mobiles. In this talk, I'm presenting a JUCE module which adds browsers to the available platform set. But first, why would you as plugin developers be interested in such a thing? Well, for motivation, web is very good for disseminating content. So if your users could just browse to your web page and try your plugin straight from their browsers without downloading or installing, I think that would be one of the benefits of running plugins online. We have already 2 pages where you can try this out. This WebAudioModules.org site is for open source demos, and the wam.fm site has a shop backend, and it is more for commercial plugins. Another motivation might be that the desktop plugin market is right now pretty saturated. So I went to Wayback Machine to look at what KVR looked at year 2000, so 18 years ago. And this was all the plugins that were available there. There are some 80 plugins or so. And I was happy to see some familiar names still there. But if you now go to KVR, there are probably thousands of plugins available. But online, it's completely the difference. There are only a couple of plugins available online, yet online door companies combined together count their user base as millions. So perhaps this could offer an additional revenue stream for you as a plugin developer. I'm associated with ampstudio.com, which is one of those online doors, and we just recently announced support for running web audio modules online. So here's the door running in desktop Chrome, and this is one of the open source plugins that I'm going to use in this talk as an example. Now this particular implementation is using web technologies for the user interface. So only the DSP part of JUCE was ported directly online. But in this talk, I've extended the component a bit so that it also includes the user interface part. Because the DSP part was really easy to port. It didn't take maybe 2 hours to max 1 day to port. But the user interface part was more tedious. So in order to streamline also that side, I ported the entire JUCE stack to WebAssembly. So how to do that? This is the outline of my talk. I'm mostly focusing on porting workflow, showing a brief demo that it actually works, then discuss about a side product of this module, which is that native plugins may also benefit this by running the user interface in WebView. More about that later. Then, before concluding, I will briefly look at what had to be changed in JUCE codebase. First, before going to the actual workflow, few words about Web Audio Platform. So, native plugin hosts like DAWs run plugins usually using two threads. Main thread runs the user interface, presets, and things like which are not real-time, whereas the audio thread takes care of hardcore DSP and MIDI. JUCE has plugin editor and plugin processor class to sort of model those architectures, and web browsers nowadays also have these different options to run in threads. So traditionally, the browsers only had single thread, which was main thread. Everything was running there. But with the latest Web Audio API additions, some browsers now offer the access to audio thread as well. So the DSP can be run in that thread. And in addition, there are things called worker threads. And there can be, I don't know actually if it's limited, but there can be a substantial number of worker threads per web page. And this is very good because Chrome next version 71 will announce support for C++ threads, and it's using these workers to do that. So having these three things gives us some leeway or different options how to or where to run these things. The first one is most obvious, running everything in main thread. And that's possible because JavaScript or the web environment is event-based. So it can model like threads using events. So this option runs in all browsers, and it's most straightforward to port. But it has some downsides. It's not as efficient because the user interface is running concurrently or is the event-based system is not good enough to run audio code without glitches. So a better option is to split part of the plugin processor here, implement it as a different module, and run it in audio thread. Then the audio can compute its DSP stuff more efficiently, and there will be less glitches. But unfortunately, in browsers, there's still one issue with this, which is that the main thread and audio thread, they both run with the same priorities. So there might still be glitches, even if they are on different threads. So just a couple of months ago, Chrome announced support for off-screen canvas, which allows us to take everything from the main thread and put it into a web worker. So the web worker would now run the user interface and the non-real-time part. The audio thread would run the DSP code, and Canvas would be just like proxying in between. And from what I've been testing, this option C is now the preferred one, at least for the things that I've tried. So I've written some boilerplate code which hides most of the complexities involved. So this is JavaScript. First, the code runs a host, gives it a place to place the canvas or the user interface. Then it creates a plugin, loads a WebAssembly module here. These awaits stand for asynchronous stuff. And once these 4 lines are ready, it can start by opening the user interface and connecting the audio output of the plugin to the system output. So this code implements the option A. For option B and C, where the audio thread is running the DSP part, the init method needs to include another WebAssembly module, which in this case only contains the plugin processor part. And then finally, for C, to offline the canvas rendering from main thread, all that is required is to use another host class. So that's pretty simple. But I also made a single liner for things so that these could be embedded easily into WordPress pages or whatever. So this actually tries to find out what's available in the browser that it's running on and chooses A, B, or C in that order accordingly. So this example is how I ported an open source plugin called OBXD to run in web browsers. I just went to GitHub and cloned the repo. OBXD was developed from JUCE 4 something, so I had to make little adjustments so that it would run in JUCE 5. And then I had to create a make file for it. And now don't panic, this is a template. So the only parts that I had to modify here are the red ones. First, a loader target, then export name, both are arbitrary names, I used OBXD. Then line 9 here lists all the source files that were included in OBXD. So plugin processor and editor, and the binary data was in res.cpp. The actual implementation was in include file or header files that went here. And then finally I just had to compile it. And that was enough to run OBXD in a web page. I didn't have to touch any of the original code base at all, so it just worked. So that would thus implement this one. For this one, to separate the plugin processor part, I had to create another make file. Here I just defined a different target name and different export name, couple of lines of boilerplate code to help for installing things, and then defining here that we don't want to use the user interface in this case at all. Then here I had to touch the OBXD code base. So in create editor call, I'm just testing this define if it's available or not. And then again make and embed it into the web page. This has now a couple of more attributes. Keys will give it a keyboard, soft keyboard, and these banks will load some URLs for default content. So I can now show a quick demo that this actually works. So this is the main thread part. And if I modify this, and it's pretty performant, even if it's running everything on main thread. The pop-ups that Olli was talking about are thus implemented with different canvases, so you will get it like this. And this came from JUCE. The separated DSP looks like this, sounds exactly the same, and then the remoted canvas thing looks like this. So to user, it's all the same. All that is changing is the efficiency of the implementation, and all this happens in background, so you don't need to care about it. And here are a couple of examples of other things that I did. This is FM synthesizer. This works exactly like the desktop version. And the last example, which is still pretty much work in progress, is Rory Walsh's Cabbage, which provides JUCE front end to C-Sound files. So what's cool with this is that with C-Sound you will get all 1,000 or so unit generators available. And another thing which is cool, in my opinion, with this is that it can change to a different plugin just by changing a preset. So I'm not here now changing to a different plugin. I'm just changing something what's in the background. All right. So when I got this implemented, I noticed that maybe this might also be useful for native plugins, because if you're using web browser component in JUCE, you cannot mingle and match that with JUCE components, because the compositing is different. So the web browser component always draws on top of the other components. But with this, it's possible to mix and match HTML elements and JUCE components. And for this, I modified the web view, or upgraded it to WebKit web view in Xcode or OS X, and introduced these new messages or methods. And this bridge here can be extended optionally with a WebSocket server to communicate with binary data directly from this native site C++ to the user interface stuff that runs in a web view. So the implementation highlights, just quickly, the static library includes these modules, and what's missing is all process and threading stuff that was not available at the time when I was developing, but I will have a look now that the web worker implementation is coming out. Sockets and named pipes are also missing, and WebGL is one of the things I would like to look at in near future. So all these changes in JUCE are in WASM namespace. And what was, in my opinion, really cool is that I really didn't need to touch JUCE codebase that much. Most of the changes were just if-defs in same places that there already are if-defs. The only thing that I really had to change was the graphics class. So I had to override draw text methods to make those virtual. That's basically all that I had to change in JUCE code. So all the functionality of web browser is proxied using these classes here, and they are separate from the JUCE code base and collected together into a single module, which can then be linked with the plugin code. So to conclude, I talked about a JUCE module which streamlines porting and enables running JUCE plugins online. And it may also help with native GUI implementations. And I noticed that JUCE platform code is really well isolated from the rest of the JUCE code base or the library. So it was possible to do this without intervention in JUCE itself. But for web, it would be really nice to split the audio processor class into controller and hardcore DSP part. That would ease up the splitting into different WebAssembly modules. I understand that in desktop this does not make much sense, but for web implementation that would be really preferred. And I found that the preferred architecture is to run DSP as a web audio module in AudioWorklet, and GUI also off main thread in using off-screen canvas, which is available in Chrome, and I think it might already be in Firefox. If it's not, it's coming soon. I also found out that the canvas-based GUIs require some CPUs. So if the web or the user interfaces were implemented using web technologies like HTML elements or SVG, then it would be much more friendly to the CPU. And also the carbon footprint would be much lower. So there's still things to do. GUI part can surely be optimized more. And I would like to add WebGL support there also. And although those plugins that I tried, they port surprisingly easily, I would still like to explore more plugins and more ports so that I can be sure that this really works as well as it seems to work. So there I would like to ask your help if you have a plugin that you would like to see running online. Please contact me in this first address, or if you're interested in the monetizing options, contact me or our CEO, Bill Bryant, in that other address. And that was it. Thank you.
Any questions?
Hi, thank you.
Hi.
That was really interesting. Do you have any sort of rough idea of performance? Like, you know, how Ollie had some rough ideas of how it compared. Did you do a comparison for ABXD or?
It's really difficult to say in general. I would say that WebAssembly is roughly in the ballpark of 50% to 75% of native implementation. It really depends on so many different things that another synthesizer might be more efficient than another. But 50 to 75, I think it's good estimate.
Seems pretty good.
Yeah, at least for online demos, it's perfect.
Yeah, cool. Thank you.
All All right, if we have no more questions, let's have say thank you again to Jari.
Thank you.